Hello. Good morning, good afternoon. My name is Mikhail Khasin. I'm Senior Manager Director from Sberbank, responsible for our core banking transformation program. And I would like to talk today with you regarding the challenges that probably most of large banks faced over the course of the last few years, and why all of them, or most of them, trying to change or re-engineer traditional banking architecture, and these banks introducing more and more in-memory computing in their stack and landscape. Actually, if you look over the course of 10, 15 years, and you see how different financial services moved from physical to digital channels, and today, more and more transactions are happened online, electronically, without any physical presence of the clients in the branches. You discover that many large banks face several challenges. They have several dramatic impacts of the environmental change. The first impact is about peak workloads. Like if you look, for example, at any large bank, like for example at Sberbank, we have about 20,000 branches in 11 time zones, right? In the past, where most of the operations happened physically, where a person was physically in the branch, even if you consider that all 20,000 branches were open simultaneously, and all branches have 5 windows serving clients at the same moment, you discover that no more than 100,000 clients were serving in a particular second. And if you also take into account that average time of the servicing client in a branch is like 3-4 minutes, you can easily calculate that the number of transactions a second during peak load was no more than 20-30 transactions a second, and it was 10 years ago. So today, when we have like about 20 or 30 million our internet clients of our mobile applications, during peak hours, they create the workload of 3,000, 4,000, 5,000 transactions a second. So you discover that over the course of just 10 years, the number of transactions a second with which our core banking platform need to cope grew up by a factor of 100. And obviously, all our current systems were built in mid-90s, right? And basically, they were built on traditional architecture and different technologies. And today, yes, we did a lot of so-called incremental re-engineering and a lot of hardware upgrade. But basically, what happens, like every year, because this number is still growing and growing, right? So more and more operations moves from physical to digital channel. And the volume during peak hours grow like 30-40% every year. So basically, every year, bank just blessing what happens earlier. Either we face performance problem during peak hours, or IBM or Oracle or Sun, right, release their newest high-end machine. And this is never-ending game. And basically, if you also count a lot of money that banks need to spend to do this hardware refresh just to cope with volume, because the traditional architecture represents vertically integrated software stack, and basically it's scale only vertically, so you need to buy more and more power machines to cope with that. You discover that basically in few years, all IT budget, if we need to keep it flat, will be spent just on hardware upgrade and regulatory changes. So the banks could not continue successfully develop and keep their market share. And because basically all smaller banks or fintech companies, they successfully implement in digital channels a lot of stuff. Of course, they have much less number of clients, but they all eating the market share from the big banks. And another big challenge is client centricity. And this is the way how we structure data and how we work with this data. And again, the problem is that in the past, because when you talk about bank with dozens of millions of clients and with hundreds of millions of accounts, basically all their system traditionally are organized by product-oriented way. Like, for example, we have one system for deposit, another system for loans, the third system for payments, etc. And again, this is common traditional architecture for all large banks. And therefore, it's nearly impossible to implement client-centric services, especially where new products are mixture or packaged products from several traditional ones. Like, for example, when your interest rate on loan depends on the amount on deposits, or when we have dynamic pricing, when, for example, we need to decide online if we charge you commission or not, again, based on your assets and based on your segments that you have with the bank. And so what happens to implement such client-centric functionality where you need to merge the data from all these huge databases from vertically product-oriented system. And again, it has huge effort, it costs a lot, and it doesn't work reliable enough. And again, with all this thing, all big banks trying to losing the competition to smaller banks and fintech companies who are successful in releasing new and new products in like months or weeks. In a bank, to implement like new package may take a year or like year and a half, etc. So banks need to react, because otherwise they're losing their business, right? So they're losing the clients. And new platform or new core banking platform should cope with new reality and new requirements that basically the market environment represents put in front of the banks. So first thing, it should be client-centric data model. It should be common data space with mostly instance access to the data. It should have a lot of instruments for machine learning mechanism, because a lot of more and more decisions the system should make automatically and online in real time during the processing the transaction or servicing the client. We should have open API, because a lot of business model change. You know, currently banks or in internet bank, people wants to buy insurance. And insurance they buy from other partners, not particularly from the banks, because once you build your internet bank on your mobile app, usually it becomes the single window for the client to the whole range of financial services. Either this particular bank supports the services, or the bank partners with somebody else. But again, all these services should be available in single window, in single application, to satisfy the client needs. Absolutely new horizons for performance. And as I mentioned today, like if we're building something new, obviously the performance we plan to support is like 30,000 or 40,000 transactions a second. And again, it's absolute requirement that the system should scale horizontally, because in new reality, any vertical scalability is the path or way to nowhere. And again, availability, it should be 24/7. In the past, when I mentioned most of the operations happened in the branches, then if branches are closed, like on Sunday or public holidays, then the banks had the time for doing batch processing, end-of-day procedures, etc. So today, when all is in internet, then availability of the system and availability to do all the transactions and provide all the services is 24/7. And plus, more and more pieces of the technology stacks move to open source. And again, the reason for that is following. It's most of the banks, large bank, has unique systems, and regardless, they were built fully in-house or partners with vendor. Finally, it's like unique copy of the product that was released specifically for the particular bank. And in this case, if you don't use much open source, again, you have a lot of different vendor dependencies that you should resolve, because finally, each vendor more focused on the product side rather than particular solution or unique solution for one client, because any technology vendor focused on building one solution or one product and sell it multiple times, rather than building some unique product and then spend years doing supporting and further development for a particular client. It's a different type of business. And basically, banks would like to have, because today the technology platform, the stack, is main competitive advantage. If you look on the banking industry, it's more like technology service, different technology services with the banking licenses, right? It's much more direct banking rather than like traditional banking. So, and having the technology stack and as a competitive advantage, banks would like to have full control of this platform, of the software. And open source solution, it's a significant contribution into this direction. So that's why banks looking on new technologies that appears during the course of the same 10, 15 years to support different technology, global technology vendors and services, because as you know, the first companies who reach like hundreds of millions of people serving simultaneously in the internet were companies like Google, Amazon, PayPal, etc. And basically the whole stack of in-memory computing appeared and matured over the course of these 10, 15 years. And therefore, looking into this direction, banks look more and more in these technologies and trying to put them and apply them for building new architecture, because as I mentioned earlier, they need to transform their core banking stack anyway. Otherwise, they just won't survive in 5, 10 years' time. Actually, what we discovered that talking about in-memory computing, there are two types of technology: in-memory databases and in-memory data grids. It's interesting that in-memory data grids, they more grown from distributed computing, where they're solving the task of parallel computing on multiple nodes, and then finally developed data layer. And in-memory databases, they originally grew from the fast data access rather than to distributed computing, and then try to scale horizontally by running multiple instances of these in-memory databases across multiple nodes. So my prediction is that very soon these two directions merge together, because if you look on the reality, like a lot of big retail companies, either banks or other ones, we need both. We need efficient in-memory distributed data layer that can cope with like hundreds and hundreds of terabytes of data, and we need very fast transaction processing on top of this data. So on this slide, this is our view on how we are building our new core banking platform. Basically, we split our vertically oriented software stack and platforms into horizontal layers, right? So on the top, you see United Frontend. This is omni-channel interface that can successfully serve our clients in any digital channels. And moreover, each functionality that we will put in place will be simultaneously available in all channels. So, and the next layer is computing layer or product layer, transaction processing layer. We need very fast transaction processing engines, or we call them product factories. Basically, the ones that produce process transactions on deposits, loans, payments, etc. And simultaneously, we need the data layer. And the data layer, this data should be in memory, because otherwise we can't achieve this performance target. And at the same time, as you know, the most efficient way is when the code that access the data and the data are on the same box. So basically, this brings us to idea also thinking about customer centricity, that we would like to have each node in our core banking architecture as a machine servicing particular list of clients. So it means that all client data to particular clients will be on this node. And this node will be able to process all transactions, everything that this list of clients needs. So, and this is the way how the system may scale horizontally. And by the way, this is the way how all technology company scales in the past, because you know they all grew from the startups, and when they were at the stage of startups, they never had money to buy these mainframes or multi-million high-end hardware. So basically what they did, they bought smaller boxes. Let's say the box was enough to process like 50,000 clients. And then when the threshold was reached, and then they have, let's say, 100,000 clients, basically what they did, they put next box to the first one, and basically they have a lot of smaller boxes processing, let's say, 50,000 clients each, but they were trying to manage them to work as a single platform, single system, and build common data space between all these nodes to be able to have kind of single database of all this data. And this is the way how we are building and designing our new system. And then, of course, underneath you have like your data warehouse platform where you keep all the historic data. So what we did, basically to start doing this implementation, we need to write the pilot, to implement the pilot. And on this slide, I present the architecture of the pilot core banking platform that we built to test on different in-memory computing technology to make the choice before we proceed with the program at full scale. So we have one primary node for each transaction processing engine. We have one primary node and two backup nodes. And so basically it's like triple resilience, right? And what we did, we upload about all our accounts, like 900 million of accounts, and trying to measure how of existing in-memory data grids can cope with such volume and how efficient they were with transaction processing. So we did a number of different tests with this pilot. We use our deposit system as an example for the pilot. So we actually used up to 8 active nodes, and we achieved like great performance result. So basically, if we talk about like, as I mentioned earlier, right, in transaction processing, today we fight for 3,000, 4,000, 5,000 transactions a second. And this is on high-end IBM machine working in 3-node real application cluster mode, right? So on 8 x86 nodes, within memory data grid, we achieve 30,000 transactions a second. So 10 times better performance than with our legacy system. We also did a number of tests based on fault tolerance and trying to see how the system behaves when some nodes goes down, and also measured some other critical for the performance operations like interest rate calculations, etc. And based on the results, we did our choice from technology perspective. We selected GridGain as a platform for both our in-memory database layer and in-memory compute layer. We selected Activity as a business process management engine, and Kafka as an enterprise service bus that can cope again with such huge number of messages a second. And in terms of hardware, it's like standard x86 hardware, approximately with 1 terabyte memory each, on which we plan to run our our core banking platform. And so we launched this program, and now we are in the progress of building our first core banking application that we plan to go live in Q1 of 2017. And now I would like to hand over to Dmitriy Setrakyan, who will tell you a bit more on technology, how GridGain technology works in our example, in our use case.
Thank you.
Thank you.
So my presentation is actually going to reload, and I think we'll have a Q&A session at the end for Mike and for me together. So save some questions that you want to ask Mike, and we will allocate about 10 minutes. All right, so I'll go fast because these two presentations are very compact. So Mike actually gave a great intro. He actually described how, a great presentation. He actually described how data grid can be applied to financial use cases from a business standpoint, and what business use cases have to be enabled on top of data grid. And I will focus a little bit slightly different because definitely I'm more involved in a data fabric development and data fabric products. So I'll focus more on the data fabric side and focus on how data fabric architecture can satisfy those use cases that are so important for financial industry. So before I start, I just want to give a brief overview of what Apache Ignite is, or what GridGain is, what in-memory data fabric is. So I'll start from explaining what difference between GridGain and Apache Ignite. So Apache Ignite is an open source Apache project. It has a very active community, very active user list. It's developed under the umbrella of Apache Software Foundation, and essentially belongs to community. Pretty much right now, there are plenty of contributors, plenty of people participating on dev list, on user list. So it's a healthy, fast-growing project in Apache family. GridGain, at GridGain, we focus on providing commercial components on top of Apache Ignite. So most of the components we provide in GridGain, we don't change Apache Ignite at all. We just enhance it. We add security capabilities. We add management and monitoring capabilities. We add cross data center application, cross rolling upgrades, and et cetera, et cetera. So most of the functionality that we add, first of all, it's probably a configuration change. So if you already started off with Apache Ignite, you would be able just to switch over and configure GridGain features on top of it. So most of the features have to do with security, management, and 24/7 availability of the cluster. So what is in-memory data fabric? The main goal of in-memory data fabric is to improve performance and scale, the performance and scalability of your application. And we do that by providing a collection of in-memory components. All of those components are independent from each other, but all of those components serve a common goal. They will, in one way or another, for their use case, they will improve either performance, scale, or both. So some of these components are data grid, compute grid, service grid. We have a streaming component. We have integration with Hadoop and Scala. So there are plenty of components here, and you would never have to use all of them. So don't be overwhelmed by the number of the components that we provide or the number of features you see in in-memory data fabric. Most of the users start out with one. And as you start out with one, you maybe actually find a use case for another. And maybe down the road, you'll use more. But we have plenty of users that use just one and two happily. The value here actually comes not from the feature set itself, but from the integration between these components. As Mike actually mentioned, it's important that processing, it's important for Sberbank, for example, that all the client data is processed on the server where the clients actually are stored. And that's exactly what this type of integration does. All our components are data aware of each other. So computation will always go to a node where the data resides. Streaming will always stream data to the nodes where the data will be eventually cached. Spark integration, Hadoop integration, service integration are all affinity aware, all data aware. So that's where the scale comes. By moving compute to the data and not the other way around, not moving data to compute, you actually achieve a great horizontal scale. A little bit about the product. It's very simple to install. It comes as a zip file. You unzip it, run a shell script to start it up, and you have one node. You run another shell script. You have another node. We focus on ease of use a lot. We add only one dependency. So the project is fully Mavenized. So you can add dependencies on a la carte basis. The main dependency we have is, one of the mandatory dependencies is JCache. We implement a JCache standard, JSR 107, and all other dependencies you would bring on a la carte basis. So if you need, for example, Spring configuration, you wouldn't add Spring dependency. If you want to use log4j for logging, you would add log4j dependency. And lastly, I'll mention that there are no hardware requirements here. They will gladly consume all the resources you make available to us. If you give us highly loaded servers with ½ terabyte of RAM and maybe 64 CPUs, or maybe low-end servers with maybe 2, 3 gigabytes of RAM and a couple of CPUs. Doesn't matter to us. We'll take what we're given and we'll try to scale your processing horizontally. This is a slightly different view on the same platform. Here we split it into transactional and analytical use cases. And as Mike mentioned, ideally, the financials actually require some combination of the two. But if you had to separate, I would say data grid, which is probably one of our biggest components, will likely be on a transactional side. However, it's also used on analytical side as well, but majority of the cases are on transactional side where you're dealing with several terabytes of data and where high performance, high throughput, hundreds of thousands of operations per second matter. On analytic, same goes for compute, which is processing computations on top of data grid, et cetera. On analytical side, we have more of a big data use case. So on the left side, I would say it's a fast data use case. On the right side, it's a big data use case. So in a big data world, latencies matter more, but big data world has to do mostly with interactive analytics. So whenever we use interactive analytics, essentially we click a button, we wait a little bit, and the response comes back. So anything under a second is fast enough because it's fast enough for a human being to perceive it as fast. However, if we actually did 1 query per second on a transactional side, our system would never scale. So ideally, we have to support low latencies and high throughput in both worlds in order to make sure that we can actually combine them, to combine transactional and analytical processing. So let's take a look at some of the use cases that are important for in-memory data fabric in financial services. Of course, I've alluded to high performance and low latencies already. And another, probably one of the critical features that financial services require is strong data consistency, strong asset compliance. Just imagine that we're moving money on top of this platform. Being eventually consistent is not good enough, right? So being sometimes consistent or temporarily inconsistent and then merging the data together whenever it comes to money is not going to work. Strong asset compliance, strong data consistency probably matter the most. Another important feature of a memory data fabric, I would say, is ability to compute on the data directly on the nodes where the data is cached. So there are many approaches and many ways to talk to distributed systems, but it's important that the approach selected has to supports sending compute to the data. So for example, if you select a solution that does only SQL, you are not sending compute to the data. You're sending data to compute because you're executing a query, getting a result back on the client side. Sending compute to the data is reverse. You're sending your logic over. A good analogy here would be a store procedure in database. So if you create a store procedure in database, it actually executes directly on the database, right? So directly on the server where the data is stored. In a distributed environment, this translates to a piece of logic, a closure, a lambda, that gets distributed, that is written by user and gets distributed within the cluster, directly on the nodes where the data resides. So having compute execute on the data is actually, in a database world, would be having a store procedure execute directly on the database server. And of course, strong querying capabilities and aggressive SLAs. Strong querying capabilities, the system has to support a commonly known query language or easy to use query language. In our case, it's SQL, and I'll talk about SQL in more depth. And also from a SLA standpoint, it's very important that the system shows resiliency. If you go through crashes, and as far as crashes go, you can have a server crash, you can have a data center crash. But in either case, whatever crashes, your system has to recover quickly. For example, if you have to load terabyte of data in memory on every server, that may take an hour. So that's not going to be acceptable from a recovery standpoint. And I'll talk about that. I'll talk how it can be supported in a distributed architecture. So we'll start by going through some of the components and focusing on some of, on architecture of those components and how they support financial use cases. So as I mentioned, data grid is probably one of the biggest components we have. It has to do with distributing data in memory, distributing data within your cluster, partitioning data. Another word probably would be sharding, although we're not really sharding data. We're partitioning data across multiple nodes in the cluster, and collectively across all the nodes, you got your data set, right? So it's a scalable approach where every node owns a portion of the data. The more data you add, the more nodes you add, the more data you can cache. And there are several ways you can talk to a data grid, and it's important that you can communicate with your data in more than one way. So first way would be key value API. So you can access it as a distributed hash map API or JCache API, essentially puts, removes, replaces, stuff you expect from a distributed data access. Second way, probably important way to access data or interact with data grid would be SQL. So you need to be able to query your data, you need to be able to join, execute distributed joins, etc. And the last way probably would be compute for join MapReduce type of communication. So in GridGain and Apache Ignite, we support all three. One thing I didn't mention or I didn't talk about yet is integration with databases, which is also fairly critical. Imagine a large bank moving to data grid architecture and just getting rid of their databases in one go. That's not going to happen. There are a lot of dependencies on existing databases, so the system has to be able to integrate with existing database and provide potentially maybe a path down the road to replace one database with one monolithic database solution, maybe with a distributed data architecture. So that's what one of the main differences, by the way, between in-memory data grid and other distributed technologies is that in in-memory data grid slides in on top of your database and beneath your application. So it's a distributed performance caching layer that can accelerate performance and improve scalability of your application. And whenever data is updated in application, it has to be written through to the database. Database becomes part of the transaction that happens in memory. It's all or nothing. And the reverse is also true. Whenever data is updated in database, it has to get into memory. So both ways are supported in GridGain. And another thing that is turned out to be very important is deadlock management. How many of you actually heard about deadlocks and know what deadlock is? All right, great. So you probably know how difficult it is to debug deadlock situations in a distributed environment. Essentially, imagine a team, imagine 5,000 developers all coding and writing to different APIs that have to do updates within in-memory data grid. So if you ask people how do you avoid deadlocks, the most common answer would be you just access the data in the same order. This way the locks are acquired in the same order. Deadlock will never happen. Accomplishing that in a distributed group of over 1,000 people is virtually impossible. There are a lot of components. All of them are going to be updating data in whatever order. And putting some control, putting some system on top of it is very difficult. So to support that use case, we actually added deadlock-free transactions. Transactions that will always that will never acquire locks. You actually do not have to worry about order of your lock acquisition, order of your data access. But every now and then, if in the cases of high contention, some transactions may fail, right? So they fail optimistically, we throw exception, and you retry. So that's the penalty for not acquiring the locks, that it can optimistically fail. However, in many cases, that's okay, because contention is not something that we see too often. It probably is less than 1% of operations. So in many cases, it's okay to have contention fail. But if you do actually have to acquire locks, then we provide deadlock detection mechanisms. So essentially, which kicks in only if transaction takes too long, if we actually suspect that a deadlock may be in place. And whenever we detect that, we will actually report all the keys that have been accessed in the reverse order. So the only way to fix a deadlock is to fix your code, essentially. Change the code to change the data access pattern. So we tell you what data was accessed, so you could easily find the code that needs to be updated. I've talked about SQL. I just want to mention that SQL and being able to query data in a common language, easy to understand language, is very important. And the ability to support SQL is probably one of the strongest features, one of the most differentiating features that Apache Ignite or GridGain have from other distributed architectures. And we are actually IMC 99 compliant. You can execute any type of queries. You can run distributed joins. You can run unions, group bys, having clauses, averages, means, what's not. So full-fledged of SQL is supported. The most importantly, probably what is the hardest thing to support, but which we do support, is distributed join. So whenever you select from more than one tables or more than one caches in data grid terms, you want to be able to do it in one query versus putting together your join manually, which is very time-consuming and does not perform. Just basic example of a SQL statement that you can execute on top of a data fabric. You can, by the way, access it from coding API, or JDBC driver, or a DBC driver, which we also provide. Basic select, but here why I like it, it does aggregations, average, max, mean. It does a join between person and organization table based on a foreign key. It does a group by, order by, so all of that is supported. From a compute side of things, it's important that essentially you can compute on top of the data that you're caching. As I mentioned, bringing compute to the data is most important. You want to be able to avoid any kind of data noise within your application, so that's the primary goal of compute. Several compute patterns that you have to be able to support. First of all, just basic closure, basic logic distribution. I have this logic, like analogous to store procedure in database. I have this piece of logic, I want to send it to the cluster, I want it to execute on the data that resides locally on those nodes, and I want to perform that logic 1,000 times per second, or maybe 10,000 times per second. So that's the basic, most common use of a compute grid. Second use case that is very common would be using fork join. Fork join is a special case of MapReduce where both mapping and reduction happen on the client side, assuming that mapping and reduction steps are very quick. Oh, what happened? Yeah. There you go. Did battery die? We have a deadlock. I have it on my laptop. Oh, there it is. They're going to bring it up. I could continue speaking, but I forgot which slide I was on. All right. OK, I was here. Thank you. So basic closure, basic logic distribution is one of them. I was talking about fork join. So fork join is a special case of MapReduce where both mapping and reduction happen on the client side, assuming that they're very fast. Fork join is probably one of the fastest ways to distribute your computation. You take a task, split it into multiple subtasks, just like it's shown on this picture. Have those subtasks execute in parallel, and send the result back and aggregate it on the client side. You utilize this approach when tasks are rather complex, right? More than just a simple computation. However, it's one of the fastest ways to actually distribute computations, distribute a single complex task over a data grid. MapReduce, on the other hand, I would not recommend using MapReduce for performance reasons. The paradigm was the architecture, MapReduce design was never meant for performance. It was mostly meant for batch processing. Essentially, if you need to take a job that takes 4 hours, maybe do it in 1 hour. It will never take a job that takes 10 seconds and execute in maybe half a second. So it's not meant for those goals. So I recommend sticking to fork join and basic closure distribution. Our system will automatically load balance all your computations. We also provide a guarantee that as long as one node is standing, if there is one alive server of GridGain or Apache Ignite, no computation will ever be lost. And with that in mind, I want to look at the Sberbank architecture, probably a bit of a, Mike had a few business use cases slides. This is more of an architecture slide. How is data fabric applied in a Sberbank use case? So essentially, you have a distributed caching layer, and you have multiple clients interacting with it. And what we have here is we will provide a shared memory layer that can process transactions in memory very fast. We partition the data in memory, and then we process the data in memory very fast. There's on-heap and off-heap memory. If you're familiar with Java, how many of you actually have ever faced a garbage collection issue in Java? All right, so you're actually familiar that solving those problems are not easy. Tuning garbage collection is not easy, and that's why we store data off-heap. If you heard Michael actually speak about Sberbank infrastructure, the average memory size on each server was about 700 gigabytes of RAM. Putting that on heap would be disastrous. You would run into garbage collection pauses probably 20, 30 minutes long in a cluster, maybe even longer, when all the cluster seems frozen and offline. So obviously not good for any type of reasonable SLA, and that's why we provide off-heap storage. There's also another component. Note how we add in a disk storage component, and that's actually very interesting. So think about the recovery case when you have a 500 node cluster, and each cluster serves about 500 gigabytes of RAM, about 100 terabytes of RAM. Think about restarting that cluster if all you can do is work from memory. Loading 500 gig on, or 700 gig on every server would probably take about at least 30, 40 minutes. And of course, again, not good for any type of SLAs. The system has to be able to recover immediately. So to solve that, we need to actually make it available to work from disk. And that actually changes the way we look at the world. Now we actually have an in-memory layer. We have a disk layer. Now we can actually have data that can live only on disk, or data that can live only in memory, or data that predominantly resides on disk and uses in memory as a caching layer for that data. And here you can actually now support gigabytes, terabytes, and petabytes of data, depending, of course, petabytes would actually mostly be on disk. So that's the architecture that is ideal for Sberbank, and essentially that's what brings me to talking about Lambda architectures, or combining fast data and big data. How many of you actually have heard about term Lambda architecture? So essentially, Lambda architecture is a way to combine, essentially, in simple terms, a way to combine performance and huge amounts of data into one platform. You maintain a smaller operational set on which you perform fast transactions, and you also maintain a larger historical set on which you can run your analytics. And ideally, the system should support both. So that's what, there are different names for this type of architecture. There is a converged data platform, then there is Lambda architecture. Gartner came up with the term hybrid transactional and analytical processing, HTAP, which I'm not sure I like the way it sounds, but it also means the same thing. It essentially means that you have to be able to compute and have to be able to transact on data that is operational, that is being transacted on right now, mission critical data, together with historical data that is maybe 10 years old. Ideally, you should be able to query between operational and transactional data, and ideally, you should be able to transact on both. So you could actually involve some historical data together with operational data in some queries or some transactions together. And that's what this Lambda architectural converged data platform should support. And from a SLA standpoint, now imagine the restart. Right now you have all these terabytes of data on disk. When you restart, system can start operating directly from disk. You do not need to load the data back in memory to start operating on the data. So system becomes operational right away. There's not even a single second spent on startup time. And as it goes, it begins to warm up. Slowly but surely, all the data actually that is being accessed will end up in memory. And we give all the knobs to turn to make sure that user can control what's in memory, what's on disk. So eventually, the system will start accelerating as it gets used more. But it goes online immediately upon any kind of crash, be that a single server crash or a whole cluster crash or a whole data center crash. Once you restart, the system is operational immediately from disk. So that's the architecture we're moving towards. We already have many components that are required for it. And we're working with Sberbank very closely on additional features. So the main focus here would be to keep always making SQL better and keep always making disk story better. So that's actually on our roadmap, and it's not that far away. Most of these features will be available this summer. And from a SQL standpoint, it's important that we don't only support queries, we also support inserts and updates done directly using SQL API. Currently, to do updates, you need to use our key value API directly or compute API. So what we want to add a capability to update and do updates, remove deletes, and inserts directly through SQL. So you could actually plug it in instead of any database and use our ODBC or JDBC driver, and your system begins to work. The integration becomes very easy if all this functionality is supported. And more disk-only data sets, we already have it in semi-beta available for testing. Queries across disk and memory. It's very important that from API standpoint, there is no difference whether data is on disk, in memory, or somewhere in between. You should be able to query and join tables between disk and memory together. That actually allows you to query operational and historical data set in one go, in one request, and this is one of the use cases that we face more and more of. More and more customers are asking for queries across multiple data sets. And of course, backups, periodic backups, snapshots, all the standard database functionality that we are used to seeing in any type of data system. So that's it, and I would like to move to questions, and I want to call Mike on the stage. So if you have questions to me or to Mike, we'll happily address them. We have about 8 more minutes. Yes?
Quick one about the preview of the GridGain 8.0. So you mentioned that GridGain is actually based upon
This?
GridGain is based
Oops.
on, here we go. Right. You mentioned on top of Apache Ignite, these GridGain 8.0 preview, or this will be available in Apache Ignite?
Good question. So a lot of this is being decided as we speak. But most, I can say with a high degree of certainty that the SQL functionality will be available on open source as part of Apache Ignite. So inserts, updates, and deletes, doing DDL and DML essentially will be available as part of Apache Ignite. Disk, the jury is still out on that. Any more questions? Yes?
I have a question regarding your, you said you're using off-heap memory. So you basically have Java layers going down to the native layers. How actually do you doing that? Are you doing the GNI or are you going unsafe?
All right, the question is how did we implement off-heap implementation? We actually used, whether we use JNI or unsafe, it's an open source. And so you can always look at the code. We're using unsafe. Yes.
Right, so basically what we went live, we put 3-node GridGain, but not for transaction processing, more for transaction monitoring. Let me explain. Let's say payments, right? So today in our legacy landscape, for payment goes through like 15 to 20 different systems, different applications. And basically, we trying to monitor how we serve our client in real time. And basically, when payment goes through each system generates messages or events. And today, like Sberbank is like largest Russian bank, average we have 15 million payments a day. And during the pass, the payment route, we have about 20 to 30 events or messages per single payment, right? So basically, we have 3-node GridGain that accumulate all these messages, and we can monitor in real time what's happening with our payments, right? And then we put SLAs, right? So let's say our SLA is that each real-time payment should go within like 10 seconds through all the systems. And basically, it means that if, for example, I pay money to another Sberbank client, within 10 seconds, like the beneficiary should get the money on his account, right? And because it's not on the grid yet, in the grid it will be instantaneous, right? So because this is what we are building the grid for. But until it's in our legacy landscape, only we can monitor if something happens and the payment within 10 seconds won't reach the beneficiary, then we have logged all the messages and can instantaneously see where the problem is. And basically we have like some intelligent machine learning mechanism on top of it that kind of calculate the timestamps, and based on that, like show to our back office people what goes wrong in the payment logic.
What is your timeline for the rest of the e-banking activities?
So overall program is for 3 years. So by the end of 2018, we plan to completely move our core banking platform to the grid. Right, so this is where we are today.
You mentioned that in your system you still need both technologies, data grid and in-memory SQL database.
Okay.
And you desire that this or vision that there will be merged in the future. What kind of functionality right now you're planning to implement with SQL database in memory, and what operations will be performed on data grid?
Okay. So just to make small correction, I'm not talking about SQL in particular. I was talking about instant access layer to the data. SQL or no SQL, it doesn't matter unless we have all applications which support non-SQL stuff, right? So today, trying to do this re-engineering, yes, we are not moving off SQL completely. We're still using GridGain SQL functionality, which, as I remember, it's based on H2 SQL engine, right? Nevertheless, it has different limitations. And basically, today, we are working closely with GridGain, trying to, first of all, enhance and shift this limitation as much as possible. And within those areas where it's not possible to achieve this, right, then we are thinking about different things what can be done, right? So one of the options that is still under consideration, so we still have image of the memory on file level, right? So it means that these files may be put as a part of HDFS file system, and then you can run Spark on top of it in order to have SQL, more sophisticated SQL queries. But basically, we're trying to separate. There is kind of short SQL or like fast SQL that we need for transaction processing, and there is another type of bulk SQL query across the whole grid for different analytics, right? And basically, again, it depends. I can't say that we agreed on all pieces of architecture, but it depends how far we're progressing with that, right? So, because basically, if computing power of the grid nodes will be enough not only to do transaction processing, but also to do this analytics, then we would think how we will merge this. If we realize that to do analytics, we need different compute power because grid compute power is not enough, then we don't need to do these SQLs on top of GridGain platform. But again, this is something that we need to decide further. If I answered your
I think
question.
we have one, like barely any time for one last question, quickly, if it's a quick one.
Yep.
Yes, go ahead.
Where can one find more information about the store? What is that?
Well, it's on our roadmap. It's being actively developed right now. So the question was, where can we find more information on Disk Store? We're planning a beta release end of June, which will come with a lot of information. So right now, it's being worked on. All right. I think we're being asked to leave. So thank you. Thanks
you.
for your questions.